Swayam Prabha. Digital India. Educated India.
Hello everyone, welcome to the lecture 10 of the course Electronic Devices and Circuits. Today we'll talk about the metal semiconductor junction. In the last lecture we started the discussion over these metal semiconductor junctions, and today we'll continue that. My name is Deepak Jain. So we have already introduced this topic and discussed about the rectifying nature of these metal semiconductor junctions, why they are so important. Today we'll revisit that quickly and we'll talk about ohmic contacts basically. So rectifying contacts are those contacts where current can flow in one direction but doesn't flow in other direction, like basically you can say case of a diode, right, something like this. So in this direction current flows, in this doesn't flow. So this is sort of a rectifying behavior, rectifying contact, and if the contact is ohmic, so it will have something like that IV characteristic following the Ohm's law. So this is very, very important because in IC there are so many components, so many interconnects are required. So we need both ohmic and rectifying contacts for different applications. So since both are different material, metal is a different material than the semiconductors, so you can say these are heterojunctions basically, not the homojunctions. So we'll talk about we'll discuss heterojunctions and how to draw these energy band diagrams when you have two different materials fused together. So in that particular case. Okay. So first let's quickly discuss what is ohmic contact. As I said, in both the direction current will follow. It's like a metal-metal contact. So it should have a linear IV characteristics in both biasing directions. So something, so you can say if I talk about ohmic contacts, so you can say linear, close to linear IV characteristics, something like this. Okay, that's the first thing. Second thing is that almost all integrated circuits needs this ohmic contact. So there is a demand for them. All ICs need ohmic contacts. Okay, that's why we are studying them. Second thing is that when there is a fusion between metal and semiconductor happens, let us say this is metal and this is semiconductor. So under what condition this ohmic contact will form? Because we already discussed rectifying contacts for metal and semiconductor case. So as a rule of thumb, you can say when the majority charge carriers move into the semiconductor, when the majority charge carriers move into the semiconductor from metal, then you can say it would be a sort of ohmic contact. Of course, we are going to talk about that in detail. What are the right conditions, what are the properties of the metal and what are the properties of the semiconductors under which it will behave like a ohmic contact. Fourth important thing is that in these metal semiconductor junction which behaves as a ohmic contact, there is no depletion region. This is easy to keep in mind because see, if you compare a metal semiconductor junction with a PN junction diode having a rectifying behavior, here also there is also depletion region, right, which is basically at the metallurgical junction and allows current in one direction, doesn't allow current in other direction. So if metal and semiconductor combination is forming a depletion region, it's going to be a rectifying junction or rectifying contact for the case where there is no depletion region is being formed between metal and semiconductor, it's going to be ohmic contact. Okay. So when this depletion region forms, when you fuse together these metal and semiconductor and their equilibrium, their Fermi energy levels align at the equilibrium, so there will be no depletion region in case of ohmic contacts between metal and semiconductors. This is important. So let's say if you are given a energy band diagram or shown, okay, there is a depletion region, there is no depletion region, you can quickly tell whether it is ohmic or non-ohmic contact. And in ohmic contacts, there can be small barrier potential, but unlike metal semiconductor one, which we discussed in last lecture, a finite barrier which doesn't allow the movement of the charge carriers from metal to the semiconductor. But here there is a small barrier which can be easily overcome by applied voltage. So these are the basic things with the ohmic contact. So now what I am going to show the conditions under which ohmic and rectifying contacts will be there for the case of metal and semiconductors, all different possibilities. So let's consider the case of metal and N-type semiconductor, and here we assume phi m is greater than phi s. In previous lecture we talked about these are the work function potential of the metal. So if we multiply it with charge, we can say amount of energy required to move the electron from metal to the out of the metal, like to the vacuum level. Similarly phi s for the semiconductor, and in this case we have assumed phi m is greater than phi s. And second case, let's say, or maybe we can take the same case here, metal N-type semiconductor again, but this time let's say phi m is smaller than the phi s. Okay. So this case would be a rectifying contact, and this will be a ohmic contact. Okay. And if I talk about metal and p-type semiconductor, and let's consider the case phi m is smaller than phi s. So again it will be a rectifying contact, and if I consider a case of metal p-type semiconductor and phi m is greater than phi s, then it will be a ohmic contact. So it is other way around, like in case of metal semiconductor, if phi m, the work function potential, is larger than the semiconductor, it would be a rectifying contact, while same if it is lower than or equal, let's say, then the semiconductor work function potential, it can be an ohmic contact. But it's the other way around in the case of metal to p-type semiconductor. If here phi s, work function potential for the semiconductor, is larger than the work function potential of metal, then it would be rectifying contact, and if it other way around, then it will be ohmic contact. So these are the four possibilities that we should keep in mind. And one more thing, like still it's not like the end of the world, like if you have a metal and N-type semiconductor and phi m is greater than phi s, that it will be always be a rectifying contact. There are certain conditions under which it is possible to convert this into a ohmic contact as well, but this is more for the generalized case, and we will discuss them in detail. Okay. So now I will draw the energy band diagrams for metal and N-type semiconductor for the both cases, phi m greater than phi s and phi s smaller than the larger than the phi m. Both the cases, rectifying and the ohmic contact. So we discussed this case in the previous lecture where phi m is greater than phi s, right? But I just want to discuss it again so that you can compare both the cases, what is happening. So it's basically what we are talking here about is a metal N-type semiconductor junction. Okay, so here we consider the case where phi m is greater than phi s. Here we consider the case phi s is greater than phi, and we are saying that this is a rectifying contact and this is ohmic contact. Okay, so let's see the case first. So we have a metal and semiconductor. So phi m is larger than phi s. What does it mean? That the electrons in the metal requires more energy than electrons in the semiconductor go to the vacuum level. So when both are separated, that's fine, but when you fuse them together, because of the equilibrium, electrons from semiconductor will move to the metal. Electrons will move from semiconductor to the metal, and since it is an n-type semiconductor full of free electrons, that's not a problem. So electrons will move from semiconductor to the metal, so there will be a charge on the metal, and we know from the basic electrostatics that in order to prevent the electric field inside the metal, charge will reside at the surface, right? But here, since there are the donor atoms in the semiconductor n-type, so because they are donating this electron, so they will have the positive charge. So there will be an accumulation of the positive charge here, something like that. So this is a depletion region. So I hope you understand why the negative charge is here only at the surface of the metal. There is no depletion region inside the metal. So it's different from a PN junction diode case where the depletion region is in the both side. Okay, so this is important to keep in mind, and the width of this depletion region would depend on how much doping is there. If you can recall from PN junction diode, if it is heavily doped, then the depletion width would be smaller. So anyways, we'll get back to that and we'll utilize that for some very important thing here. Now if we consider the case, second case, ohmic contact case, where phi s is larger than the phi m. So here again we have a metal and semiconductor. So what will happen here? What this tell us, this phi m smaller than phi s, that for electrons in the semiconductor, it requires more energy to reach the vacuum level than the metals. Okay, so what is going to happen, that electrons will move from metal to the semiconductor this time. So metal will have positive charge because it is losing electrons, and semiconductor is having negative charge. But there is no depletion region, right? Because there is no depletion. Here there is a depletion of electrons. Electrons are being lost and going to the metal, and these ions which have donated those electrons have the positive charge. Here there is no such depletion, just additional electrons are here. Okay, so that's why there is a no depletion region. That is, you need to keep in mind that there is a no depletion region. There is a positive charge, there is a negative charge, that's it, no depletion region. So that's the difference it makes, phi m larger than phi s, phi m smaller than the phi s. Okay, that's very, very important. Now we will draw the band diagrams, band gap diagrams, and we'll show why it is having a rectifying behavior and why it is having a ohmic behavior. So okay, so let me draw the diagram for this. This is Fermi energy level for the metal, EFM. This is the vacuum level, and vacuum level will be same for both the metal and semiconductor in equilibrium. Before the fusion happens, but it can also bend when there is a equilibrium. Okay, so now it is continuous before the fusion happens. So let's assuming the continuity here. This is phi m q, and since we are considering the case where phi m is greater than phi s, so our Fermi energy level would be higher for the semiconductor. Let's say this is EFS. Okay. Since it's an n-type semiconductor, so conduction band would be at a higher place, something like that, and EV would be somewhere here, right? And this difference is Q phi S, and this is basically Q chi. Okay. So this is the scenario before fusion happens. Now both are being brought in contact together. So of fusion, after the fusion, a metallurgical junction will be there, thermal equilibrium will be achieved, and during that thermal equilibrium, this happens, that electrons will start moving from semiconductor to the metal, and there will be a barrier will be created, and that will stop the further diffusion. So in thermal equilibrium, this Fermi energy levels will aligned. So let me just draw it quickly here. I have limited space because I want to do that here only for p-type case. So this Fermi energy level will align EFS. So in order to align this Fermi energy level, so the energy levels will go down. So EV would be here, EC will be here. Okay. So in order to meet, this will be something like that. So this is EFM. So this barrier would be equal to Q phi M minus phi S, right? And this is equal to Q phi M minus chi. Now what will happen? This is the equilibrium case, and this is the case before fusion, or you can say before the metallurgical junction forms. So here this barrier Q phi B, this barrier height is there. So this is what we discussed in the last lecture, that even if you apply a forward bias or a reverse bias with respect to this n-type semiconductor, so what forward bias will do, it will reduce this barrier for electrons. So electron can sweep from semiconductor to the metal as we have this forward bias voltage. But if we apply reverse bias, this will go further down, right? This will go further down. So there will be no movement. So it's a unidirectional kind of a thing. On the contrary, from metal to semiconductor, this barrier potential is always there, and no electron will move from there to there in such a scenario. Now the question comes, if phi m is larger than phi s, so it is always the case that there is no circumstances under which it can become an ohmic contact and somehow we can overcome this barrier potential. Answer is yes, and we are going to discuss it later on in this lecture only. But let's first move to the p-type case, where we have n-type case only, but the other case where we have phi s is larger than the phi m. So let's see what is happening here. How it is different from this case to this case. So here we have already seen there is no depletion region. Okay. So now let's consider the case where we draw these diagrams before the fusion of both the P and N, and then we will discuss the case of thermal equilibrium. Okay. So let me draw this one. So this is EFM, right? And since now phi s is larger than phi m, let's say this is the vacuum level, and this comes out to be Q phi m. This is my EFS. So this is Q phi s. Okay. Since again it is an n-type semiconductor only, so this is going to be closer to the EC conduction band. and little far from the EV. So this is the scenario, basically you can say. This is Q chi. Okay. So the difference here, if you compare this case with this case, is that here phi m is larger than phi s. So what happens, the electron energy levels of these bands go down in order to align. Here it's going to go up, right? So electrons are moving from metal to the semiconductor in this case initially, just as soon as you bring them together to attain the thermal equilibrium. Here it's the other way around, that the electrons are moving from semiconductor to the metal. So what will happen here, this Fermi energy level and these levels will shift up. Okay, so if I just draw it here, this is EFM, so this level will shift here, EFS, and here there is no depletion region. If I say this is the depletion region here, this region is the depletion region where we have these bendings. Okay, this W. Here once you fuse them together, there is no depletion region, so the bends will be very sharp here compared to the this case. You see W here, so bend will be very sharp here, something like this, EV and EC, EFS, EC. So if I say, is there a barrier potential? Yes, there is a barrier potential for electron to move. As you can see from here, because electric field is here, right, in this direction from positive to negative, so that will stop the further fusion of electron from metal to the semiconductor. And since I have assumed that phi m is smaller than phi s and smaller than chi, so if I calculate the potential, this work function difference, that would be Q chi minus phi m. This is for this case, and with respect to the same level, this would be phi Q phi s minus phi m, something like that. So now we want to discuss what's going to happen if we apply forward bias and reverse bias. Okay, with respect to metal, let's say, whether it will conduct in both the directions or only in this direction. Here, if you look at the band diagrams of this case and this case, the difference is that there is a solid barrier height. Okay, in this case, here that barrier height is not there, though it looks a bit larger here just because of my poor drawing. Otherwise, normally it is much larger than this one. So let's see what happens in the case when we apply external potential. So let's discuss first case where positive bias is there with respect to the metal side, and then we discuss the case where there is a negative bias to the semiconductor side. Or I can say, sorry, negative bias to the metal side or positive bias to the semiconductor side. So what will happen? So going back, these are the band diagrams, and from the previous lectures we know that in direction of applied electric field, the band moves this way. They are increasing, the energy is increasing, because for electrons, because these bands have been drawn for electrons, so they want to move, electrons want to move against the electric field, right? If you somehow can push them in the direction of the electric field, their energies are increasing. So if, let's say, I apply a positive bias to this one, something like this, so I'm adding on this, right, adding on this one, so these will bend this way. So for example, the band diagram will look like something like this. right? So rather than being straight going this way, it will go this way. Okay, it will go this way. This is EC, this is EV, this is EFM. So now electrons which have moved from metal to semiconductors can come back. Electrons can come back from semiconductor to metal, right? So current is possible, formation of current is possible. Now if we consider the other direction, what will happen if we are applying negative bias? The electric field would be in this direction, right? So here electric field is in this direction. Here electric field will be in this direction. So these band will go in other direction. So you will have something like this. This is EC, EV, EFM. Now electron can drift from here to here easily, no problem. Okay. So it shows that this combination of metal and semiconductor with this condition, metal and N-type semiconductor very precisely, under the condition where phi m is smaller than phi s, conducts in both direction and represents a case of ohmic contact. This is a ohmic contact. Okay, so that's basically an example, and you can see depending on the material properties how the characteristics will differ. It can form a ohmic contact or a rectifying contact depending on what is the difference between phi m and the phi s. I hope you could understand a bit of that. Now I will talk about, or maybe before I talk about under what condition this rectifying behavior can be converted into an ohmic contact in the case of metal and N-type semiconductor where phi m is larger than phi s. So basically here, like if somehow what we can do about this depletion width so that electrons can drift or tunnel from here to here. So we'll talk about that. But before we do so, let's talk more about this case, about these band diagrams, what is happening in both the cases. Let's see it from a perspective of the electrons, how things are happening, why it is so easy to have current in this case in both the direction, and why it is not possible in that case. So let's first consider the case of the same metal N-type semiconductor, phi m smaller than phi s. Here the case of phi m larger than phi s, metal and N-type semiconductor. Okay, so let's see this case. Now I will draw the electrons more. So this is Fermi energy level, this is the conduction, let's say conductor case. So lots of electron, and again few electrons, good number of electrons basically above the conduction, above the Fermi energy level. And if I draw the vacuum level here, it is something like that, and this difference, this is basically phi m, q phi m. Okay. Now if I do the same for semiconductor, N-type semiconductor, and since phi m is smaller than phi s, so let's say this is conduction band and my Fermi energy level is closer to the conduction band, and this is my valence band. And what will happen if we fuse that together? Fermi energy levels will align. So it will be something like this. this is the, let's say, Fermi energy level for both the cases. This would be something conduction band, this would be of valence band. Okay. So electrons are here, as you can see, above the Fermi energy level in the conduction band. It is also full. And similarly, you have electrons here because of the flow from metal to semiconductor. So if you see this picture, it is very obvious that there is a possibility of propagation of electrons from metal to semiconductor and semiconductor to metal. While let's consider the case of metal to n-type semiconductor where phi m is larger than phi s. So what happens here, that same metal is same without any change. This is EF. Here, because phi m is larger than phi s, this is EFS, this is EFM. Conduction band is here, let's say, and valence band is here. So there are electrons in the conduction band. Once we fuse them together, what we get is something like this. If I just say Fermi energy level for both, right? This is the depletion region I'm talking about, W. So there are electrons here, electrons here. So electrons are here, but because of this barrier and this depletion region, this cannot be overcome and there is no current in this direction. Okay. Diffusion can take place from here to here. This barrier can be overcome with the application of forward bias. These electrons can come from here to here, but no current in this direction. No current in this direction. Because of this finite barrier. Right. On the contrary, there is no such barrier is there. Such substantial, very small barrier is there, not such a big one compared to here. So it's fairly easy to have current in this case in both the directions compared to here. Now, as I said, like there is some condition under which current can be there, and it can be an ohmic contact in case of reverse bias. So what is that condition, right? So the problem here is this barrier basically. If you see that electrons cannot overcome this barrier, but what if we reduce the size of this barrier, right? If we make it thinner rather than this W. So as I said, like even if you apply the voltage in either direction, this cannot be changed. But if we change the material property despite phi m greater than phi s, so if you can recall from p-n junction diode case, if it is heavily doped, then depletion would be smaller, right? Because in a small region, let me consider the case of metal semiconductor. So this is, let's say, metal, this is semiconductor, and this is N type. And similarly, we have metal semiconductor case. Here it is N plus type. Okay. So more doping. If let's say phi m is greater than phi s, so what is happening here, that electron from semiconductor will go to the metal, we will have the positive charge. Right. Things are same here, let's say phi m is greater than phi s, but this is N type, right? More number of dopants are there. In order to satisfy, let's say, same number of electron has moved, from this into this region. These are the same number of electrons here. The same charge will be accumulated here, but it is more doped, right? So more number of dopants are there compared to this one. So this depletion width here would be fairly small compared to this case. So W dash would be much smaller than W because this side is heavily doped and this is lightly doped compared to that. So under these circumstances, what will happen? The barrier that is there, this barrier will become thinner, okay? And that may help somehow to diffuse the electron from here to here. So that's the important thing. But still the question is that barrier remains, right? Okay, you can reduce the thickness of this barrier, right? But still barrier remains. So now something which we are gifted with is tunneling process, okay? So what happens in tunneling? It's a quantum mechanics phenomena. There is no classical analog of this. So it's a quantum, you can say quantum phenomenon. No classical analog of this exists. So what is happening here? So what is tunneling? Tunneling says that whenever there is a potential barrier of some finite width and height, right? So the probability of that existence of the electron cannot abruptly end. It will continue, something like this. It will continue, okay? So this basically allows the tunneling of electron from here to here, but under the condition that these barrier potential phi h or width of that need to be small enough for tunneling to happen. So we can exploit this tunneling here in this case by using very small thin depletion region by controlling the doping, and we can convert this metal semiconductor junction having metal semiconductor junction and type case heavy doping despite having phi m larger than phi s, we can have an ohmic contact, okay? Using, and what it will exploit will be the tunneling, based on the tunneling, quantum tunneling. So the conditions are here is that this tunneling distance is d, small d or w whatever. So this can be small only when there is a having doping, and the basis of this quantum tunneling or quantum mechanical tunneling, whatever you want to say, it's bound to the uncertainty principle. It says that if the barrier is sufficiently thin, we cannot say that with certainty that particle will stay only on that side. It can also be other side. The condition is that it has to be thin enough. So, or you can say in other words a wave function, if you treat electron as a wave here, so the wave function cannot abruptly end immediately, right? So rather decrease exponentially. So you can say wave function for electron cannot end abruptly, rather it decreases exponentially. Okay, so rather it decreases exponentially. So that's in terms of wave function, or if you treat it as a particle, So if barrier is thin enough, so there are, because of uncertainty principle, you cannot say with certainty that the particle will exist only on the one side. So cannot say with certainty that particle will exist only on one side. So if it is wave function, something like that, this barrier is there, some probability has to be there, right? And there's no classical analog, as I said, for this tunneling exists. So this is the reason why we can still convert them to the ohmic contact. And this technique of tunneling has been used in many electronic devices, tunneling diodes, Schottky barriers, MOSFETs, quantum cascaded lasers. So it is being heavily used throughout that. And when I was drawing these barrier potential to be like this, but in reality they can be of triangular shape, parabolic shape. In fact, here you can see they are of like triangular shape, close to triangular shape, right? So now I will talk like how this Schottky behavior converts into ohmic contact for this metal to n-type semiconductor case. Okay, and I will show how this diagram changes. So let's consider the first case of low doping, then the medium doping, and third case is of heavy doping. So in low doping, let's say this is the Fermi energy level for both the cases in thermal equilibrium situation, and this is the barrier potential EC EV. So if I draw IV characteristics, it would be something like this. IV, this is a typical Schottky behavior. Now if we increase the doping, assuming this is a case of metal to n-type case, so and phi m is greater than phi s, we increase the doping in this case. So what we will get is, if I just try to draw on the same scale, this width has gone down, right? This width has gone down. So here in the other direction, it will go closer to the ohmic behavior, right? So this would be very, very thin. And then tunneling can happen here. So the characteristic it will have is IV, nearly a ohmic behavior in both the direction. Okay, so now the take home message from here is that if you have n plus region with the metal, despite having phi m larger than phi s, it can be still be a ohmic contact because of the tunneling phenomena. Okay, so now before we move to the next topic, I will also talk about the p-type junctions. Let's quickly have a look when it will be rectifying and when it will be ohmic, if there is a metal semiconductor, but semiconductor is p-type in this case. So here the connection is between metal and p-type semiconductors. So we will discuss both the cases. Again, phi m greater than phi s, phi m smaller than phi s. Okay, it's the other way around. Phi m greater than phi s will lead to the formation of sorry, phi, let's consider the case this side, this way, phi m smaller than phi s, that will lead to the formation of rectifying behavior, and this will lead to the case of the ohmic contact. So it's the other way around, right? So phi m greater than phi s in this case leads to the rectifying one, and phi m smaller than phi s leads to the ohmic contact. So here it's the other way around. So let's have a quick look at both of that, and then we will move to the next topic. So let me just draw this case. This is EFM. Here phi m is smaller than phi s. This is the vacuum level. So this is Q phi m, and if I just, since phi s is larger, so let's say this E phi s, this is a p-type semiconductor. Please keep in mind the other cases were n-type semiconductors. So here it would be closer to the valence band. This is EFC, sorry, EC. So this is Q chi, and this is Q phi s, right? This is the perfect example. Now what will happen in this case, that the Fermi energy level will shift up, these energy levels, the energies will increase. Also, if we just see what is happening here, this is metal, this is semiconductor, right? So depletion region will form here because phi m is smaller than phi s. So electron can easily move from metal to the semiconductor, and this will attain the negative charge, and this will be depleted because this is p-type, right? This is p-type. So holes will be depleted of, this region will be depleted of the holes because electrons have come and they have recombined with that, and charge is negative because electrons has been absorbed. Here it will be positive charge. So this should not be confused with the case of metal n-type one, the same situation, phi m, phi s. There was no depletion region despite the negative charge, right? There was no depletion region if you see carefully. So if you look at this case, so here electrons are moving from metal to the semiconductor, but this semiconductor is already n-type, it's full of electrons, so these are additional electrons. There is no depletion of the charge carriers. On the contrary, here there are holes, like it's a p-type, so holes are being occupied by these electrons, so this region is depleted of these holes, charge carriers were there. So that's why you have again a depletion region, which is a sign of rectifying contact. So now what I will do, I will take it up, align this Fermi energy level, and let's see what we get. Is something like this. EV will come here, right? And remember we have the W region here. So similarly EC will shift. Let's connect them. Right, so this potential difference is there. So this potential difference is there, which is equal to Q phi s minus Q phi m. So this is the contact potential. Sorry, V naught. Right. So what is happening, that this barrier doesn't allow the electron to move from here to here, but holes can move. Holes can go this way to this way depending on the bias applied. Okay, so forward bias and reverse bias again. So this barrier for holes will decrease. On the contrary, in the reverse bias this will increase, right? But this barrier will remain. So again we got this metal to semiconductor barrier here. Again, how to reduce it? By doing the heavy doping towards the p side, so that can help. Basically large number of electron holes will be there, so this region will be small enough, right? This region can be small enough. Same technique can be applied here. Now coming to the ohmic contact case, so phi m is larger than phi s. So what will happen here? This will have the negative charge, positive charge. Okay. So now phi m is greater than phi s. It's the other way around. So let's say this is vacuum level, and this is q phi m, and for this is EFM. Here it will be, since phi m is larger than phi s, so it will be something like this, E phi s. This is a p type one, so this is EFV and this is EFC. Okay, and the difference here would be q phi s, it is q chi. Okay, so these will align, so these energy levels will come down, and in thermal equilibrium it will look like something like this. This is EFM, this is EFS. EC, and this would be somewhere closer to q phi m minus q phi c. So again, here there is no significant barrier potential from metal to semiconductor, and as you can see from these energy band diagrams, so again it will be band here and there, as we discussed in the previous case of metal to n-type semiconductor, and it will have the flow of electrons in both the directions, right, and it can have the current. So there is no such barrier potential here. So this will form a ohmic contact. So this way we have completed this metal to p-type semiconductors, and we have proved this is sort of an ohmic contact. So depending on the properties of the material that are being used, one can have a good ohmic contact. So the one lesson that we learned, that if we do the heavy doping of this semiconductor, we can have a good ohmic contact. Even if the barrier exists, the width can be small enough so that the charge carriers can travel through the barriers. So now I will talk about the last topic of this lecture, which is heterojunction, quickly. So drawing these energy band diagrams, as you can see, I keep drawing these energy band diagrams, and that gives a lot of information to us, like whether the electron will flow or not. So how can we draw that? Okay, so let's consider a case where we have two different semiconductors. It's the C1, E1, and let's say the first one is the N-type one, and this is P-type one. So this is EF1, this is EF2, E1, EV2, EC2. So what are we going to do? Like, let's say this is before the fusion together. So how to draw these band diagrams in thermal equilibrium? So step one is like align the Fermi energy levels, right? So, and before even doing the Fermi energy levels, you can calculate the delta EC, the difference between the conduction bands, right? So here it is delta EC1 minus delta EC2. If I just represent it on a scale, something like that, 1 to 2, right? On the contrary, delta EV here is EV2 minus EV1, which can be represented like this one, V2 minus V1. Okay, it can be written as C1 C2. Okay. So now this is, you can say, step 1, step 2, that we align the Fermi energy level. So this is something like this, this is something like this, this is something like this is something like this. So this is EC2, EV2, this is now a joint sort of Fermi energy level for both the cases. Now what we can do, or maybe since this is fairly close to this one, so this should be slightly up, right? So now what we can do, we can bring these differences here. So we know that C1 is here and C2 is here. Similarly here V2 is upward and V1 is here. So what we can connect basically, so this is E1, not, so we will just connect them together, V1 to V1, V2 to V2, something like this, let's assume it's bit up, C1 to C1 and this C2 to C2. So you see here, this goes this way, then there is a barrier, it goes this way, right, up, down. On the contrary, this can go this way. So this is, let's say, your step 3, okay. So step 1 is you calculate EC minus E1 and difference between these conduction bands energies and valence band energies, okay. Depending on which is higher and which is lower, you can calculate that, align the Fermi energy level, and then you can join C1 to C1, C2 to C2, V1 to V1 and V2 to V2. This way you can get the energy band diagram for heterojunction. I covered this because we discussed this metal semiconductor junction, and if you look at more higher devices, especially for optoelectronics applications, you will find different type of semiconductors are being fused together. So this is required there. So if I summarize what we did today, so the take home message is that metal semiconductor junction can be rectifying, can be ohmic, okay. So they can be both rectifying or ohmic, depends on the relation between phi m, phi s. Also depends on the doping level. Like doping level is very, very important. If P or P plus or N or N plus region, right? So doping, high doping can lead to tunneling. And can convert a rectifying contact into ohmic contact. Ohmic contacts don't have depletion region, doesn't have any depletion region, while rectifying contact do have contacts have these depletion regions. So this is the major difference that one should keep into the mind. So while in IC circuits, you can, if you dope heavily, the good quality ohmic contacts can be formed. So good quality ohmic contacts can be formed by heavily doping the semiconductor. And we also discussed the procedure of like how to make these energy band diagrams. I hope you could understand somewhat about metal semiconductor junctions. Thank you. In next lecture, we will move to the applications of the PN junction diodes. Thank you very much.